So thank you, and good afternoon. I'm very glad to be here, and today I'm going to talking about SW-RASP. So it's a Java application runtime self-protection program. So in today's landscape of cyber attacks, attackers often exploit zero-day or undisclosed one-day vulnerabilities to breach the internal network of Fortune 500 companies. They frequently utilize remote control tools like web share. And as we know, developers will also encrypt traffic before transmission to enhance the security. So the traditional WAF often struggle to handle encrypted traffic. It will run into the troubles once the attacker's traffic is encrypted. So to address these challenges, we propose a novel runtime defense technology known as SW-RASP. So SW-RASP is a Java application runtime self-protection technique capable of intercepting unknown network attacks. By leveraging JVMTI-based technology to hook into the JDK underlying logic, SW-RASP can intercept command injection attacks, arbitrary file upload attacks, and detect web shell connections. Additionally, SW-RASP utilizes ASM syntax tree to identify malicious operations, achieving a 99% interception rate of malicious activities. So compared to the traditional WAF solution, SW-RASP offers superior protection by not only inspecting the traffic, but also diving into the underlying logic of the applications. So therefore, we recommend replacing the traditional WAF with the SW-RASP to elevate the enterprise security posture. So here is my brief introduction, and my name is Ming, and I serve as the Chief Technical Officer at Shanghai Series Information Technology, and I'm focusing on the field of network security and artificial intelligence. I'm also the director of the Network Security Science Laboratory built by Series and the Shanghai Jiaotong University. So currently, I'm focusing on the trusted chip security. And today, I'm going to divide this presentation into 3 parts, so which will cover the entire process of our research. So first, why we propose a new application security solution. As we know, as a large-scale enterprise, we face hundreds of attempted hacker institutions each month within our actual network environment. So initially, we adopted WAFs as our primary line of defense, resulting in an instance reduction of hacker institution probably by about 80%. However, the remaining 20% continue to pose a challenge. So after diving deeper into the detection principles of WAFs, we identified significant limitations. For instance, WAFs operate on rule-based detection and are able to adapt to encrypt the traffic. So hacker can easily bypass WAFs by utilizing various string encoding, so-called semantic obfuscation, or corrupting malformed HTTP requests, which will leaving our server vulnerable to attacks. So in the forthcoming discussion, I will explain in details of the limitation of the traditional WAFs. So firstly, let's assume there is a command execution vulnerability in our API backend. We have deployed a WAF on the API server. When a hacker tests this API endpoint, they input a command, such as command /c who am I, and send this request. So before processing with this request, it undergoes the inspection by the WAF. So after receiving a request, the WAF will utilize its built-in rule set to examine whether the request contains malicious payloads. So for instance, it deploys regular expression to detect attacks such as circle injection, command injection, and so on. So in this case, the WAF detects the command injection in the hacker request and successfully block it. So sounds ideal. However, reality often proves to be more complex than our imagination. In the actual hacker attacks, hacker can bypass WAF by discovering the website's real IP address and accessing it directly to bypass the protection. They can also utilize the parsing differences of the different circle engines to evade WAF rules. Additionally, hackers also utilize differences in HTTP protocol IFC specification to bypass the WAF. So to address these differences and the issue of the information asymmetry, we have begun researching runtime self-protection mechanism for the applications. So to address the issues such as bypassing the WAF through the encrypted traffic and the rule evasion, I re-examined the ecosystem surrounding JVM and discovered that JVM provides functionalities for hot reloading the application code at runtime. This technology is known as JVMTI and Java Agent. We can utilize Java Agent technology to implement a self-protection program for the application runtime. So before we dive into the research, let's first understand the Java program compilation process. So prior to the compilation, a Java program undergoes the lexical analysis to verify the code effectiveness and the syntax analysis to validate the code legality, resulting in the generation of the Java class bytecode for execution by the JVM virtual machine. So the Java agent can reload already loaded class at runtime and allow you to modify them. For example, before the program output hello world, you can use the Java ASM technology to insert 3 bytecode instructions into the main method. This new bytecode will output hello, I'm a Java agent when the main method is executed. So afterward, you can use the ASM library to obtain the modified complete class bytecode and apply the modified bytecode to the running Java process through a Java agent. So due to the necessity of the utilizing the bytecode modification technique for vulnerability interception, so we need to capture all the parameters controlled by the potential attacks before the application code executed. These parameters must be gathered for subsequent RASP detection purpose. So for example, we have to find the start point of the request context. And because some application use the encrypted traffic to protect the user data, so we also need to decrypt the traffic and also need to verify all the parameters which pass into the applications. So having understood the knowledge required for writing RASP, so now we can get started to develop the RASP defense program. We will leverage Java Agent technology to build a powerful tool for intercepting the hacker attacks. So the attacks use malformed traffic to bypass the WAF, but RASP can address these issues because following reasons. So first, the RASP program starts collecting information and functions after the initialization of the web container, so it's unaffected by the malformed traffic. And even if the traffic is encrypted, RASP program collection remains unaffected, and we also will hook the sensitive APIs and initiate checks when the application executes these APIs. So firstly, we collect all the data that could potentially be controlled by a hacker, such as request headers, request bodies, class bytecode, and the call stack of the sensitive functions. So with this foundational data, we can analyze whether the data to be executed before executing circle statement or command is correct and whether it has been attacked. This is a demonstrating of a circle injection where the hacker exploits a circle injection vulnerability to attack the API for querying information. The application, after receiving the user input parameters, perform a circle concatenation, resulting in a circle injection vulnerability that allows the hackers to access all the contents in the database. So the main reason for the hacker successfully attack was that the Java backend application concatenates circle statement when executing circle queries. So after being attacked by the hacker, the circle syntax tree contains 5 unknown tokens. So to identify these 5 unknown tokens, we need to pass the circle into a syntax tree and then traverse the entire circle syntax tree to see if there are expressions or conditions originating from the attacker's input. If the token comes from the user input, it indicates that the program might be compromised by a hacker. So during our validation of the entire circle syntax tree, we found that there were redundant tokens in the circle statement during the condition filtering process, and several tokens were influenced by the hacker input. This situation indicates the presence of the circle injection vulnerability in the backend code. So therefore, we can terminate the request to intercept the hacker's attack. So based on the previous attack scenarios and the impact of the changes of the circle syntax tree, we can develop a RASP program. So first, we need to hook all the methods in the Java application that will execute the circle statement, such as the execute query, and the execute update, and so on. Then, before executing the circle statement, we will retrieve the circle statement to be executed and perform the lexical analysis to pass it into the syntax tree. Subsequently, we will validate whether the tokens in the circle syntax tree contains the attacker's input data. And this is another example demonstrating a command injection vulnerability. In this backend code, cmd/c ping is concatenated with the user input IP address to check the network connectivity. So in this example, the attackers input IP address and CAC. Due to the vulnerabilities in the backend application, after the execution of the ping command, the server will also execute the CAC program. So we performed the lexical analysis on the backend. On the backend, in the operating system, contents enclosed in the quotes is treated as parameters. Therefore, after the lexical parsing here, we obtain 3 tokens with no additional tokens added. So while still the hacker can succeed in their attacks. So after converting this command into a syntax tree through the lexical analysis, we found that the executed program is CMD. The parameter following the CMD will be treated as a command group for execution. So similar to the command interpreters like bash in the Linux. So therefore, we also need to determine where the executed program is a command interpreters. If it is, we will further pass the subsequent parameters into a subtree. So by traversing all the trees and checking for any abnormal tokens, we can effectively intercept the exploit behavior. So this is for the web shell demo. So in the hacker attacks, web shell is a common used attack method. Hackers can upload web shells to execute system command and control servers. To intercept the web shells without affecting normal applications, we can retrieve the loaded class bytecode when loading script file like JSP and analyze it. So by analyzing the bytecode, we can determine if there is a malicious content, such as the command execution or arbitrary file reading. So we utilize the Java agent to hook into the Java bytecode loading process through the class loader. So before the malicious bytecode is loaded, we retrieve the bytecode being loaded. Then we use the ASM library to pass the bytecode and traverse it to determine if there is any malicious invocations. If malicious invocations are found, we halt the bytecode loading process and throw an exception to indicating a loading error. And in the recent years, there has been a growing trend in exporting JNDI vulnerabilities. So primarily due to the log4j vulnerability that emerged a few years ago. So leading to the attacks on almost all the applications that are using this logging library. So the solution to this problem is quite simple. So first, examine the core stack of the JNDI related protocols as they finally involve the socket connect method, since the JNDI needs to connect to the external servers. So interception JNDI injection is also straightforward. After establishing a network connection, we examine whether the core stack of the socket connection originates from the JNDI related protocols. If so, we inspect the connection address and to verify if it originates from the hacker input. Additionally, considering that our applications are typically deployed within our intranets, so even if they rely on the JNDI-related APIs, we can configure RASP to intercept all the socket connections from the JNDI to external servers. Here is a demonstration video showing the distinction between the unprotected and the protected environment. So first, we will demonstrate the scenario where the application is vulnerable to hacker attack before being protected by the RASP. So first, let's conduct the log4j vulnerability test. So the hacker can successfully execute the operating system command. Next, we test the socket injection vulnerability. So the hacker can access all the database from content in the database. Yeah, this is for the command injection. And then we will test the arbitrary file reading. Yeah, now it's for the arbitrary file writing vulnerability. So next, we test the web share. And last, we test the cross-site scripting vulnerability. So the malicious script code is successfully executed. And next, we will show the impact of the application being safeguarded by the SW-RASP. So the first, we will run this program. Now we will test the log4j vulnerability. And as we can see, the RASP can successfully prevent the hackers from export the log4j vulnerability. Yeah, next we test the socket injection. And now for the command injection. And this is for the arbitrary file reading and arbitrary file writing. And then we continue with the web share. And the last is for the cross-site scripting. So as we can see, the RASP can prevent the hackers to attack the applications. So with the powerful Java agent technology, we have successfully implemented RASP and hook into the underlying APIs of the programming languages for malicious checks. So to hackers, we can confidently say, bring it on, I'm not afraid of you. So if you are interested in the implementation of the self-protection program, we have open sourced the code on GitHub. So everyone is welcome to contribute and make it even better. So that's all for my today's talk, and thank you.
All right. Thank you very much from Ming Hu for a very informative talk. Do we have any questions from the audience? All right. Okay, just a moment. Would you mind standing? Thank you.
Hello. Thank you for your talk. I have a question. Like, how implementing this SW-RASP will affect the performance of the app? If you have an existing application and you want to implement your technology, how it will affect the performance of the application after that, and will it affect it?
You mean how it affect its performance?
Yeah,
right?
how much more resources you will need, or how like it will be slower maybe.
So So it depends because there are a few use cases I just mentioned. So usually we just focus on the SQL injection, command injection. So we should do a check if there is any input data from the user input. So if the input data is from user input, then we have to apply the RASP to do the more check. So usually, if it's based on the program, how much code you from the user input. If you don't have much user input, I think the performance impact is very, very low. Yeah.
Thank you.
Yeah. Okay.
All right. Any other questions from the audience? All right. Just a moment.
Thank you for the great talk. And can your concept on this Java apply to other programming language like Go and Rust? And I believe that this technique is signature based. So because you have to perform the lexical analysis based on each attack. So what if the vulnerability is related to like business logic? Can this technique apply as well?
You mean if the logic is related to the business logic, right?
Yes.
So actually, we are not focusing on the business logic itself. So we're just focusing on the data, where the data comes from. So for example, for the SQL injection and the command injection, if the data is come from the user input, then we need to do the double check. If the data, I mean the SQL statement is in the program itself, then we don't do the check.